All right, so the equation that you have always done are called rectangular. That's probably never been explained to you before, but that's what those are called. They're called rectangular equations. And so you have y in terms of x. Usually that's the way it is. Like you have y equals, and then, I don't know, x squared plus 3x, or y equals ln of x, or whatever. But you could also have x in terms of y. And we did some of those when we did the, do you remember the volumes of the solids of revolution? Like when you had the dy problems, remember how it was x equals and you had stuff with y? It wasn't a function, but that was fine. But anyway, that's what rectangular is. You have an x and you have a y, and they're in terms of each other somehow. Those are the ones that you've always done, okay? So a parametric equation means both x and y are in terms of what's called a parameter, if I could spell correctly here. Which is called t. So you have x of t and y of t. Technically, you have sort of already done something like this when we did related rates. Do you remember how every single variable was with respect to time and they all had a dt, dx dt, dy dt? It's like that, okay? So it's not actually really something new. You have x in terms of t and y in terms of t. All right, if you want to get rid of the parameter and turn it back into rectangular, you're going to solve for t in one equation. Solve for t, and it doesn't matter which one. You want to go for the one that it's easiest to do. Solve for t in one equation, and then substitute into the other. You're getting rid of the t, in other words. So you get t equals in one equation, and then take that and substitute it into the other one, and it'll like go away. All right, so we're going to draw a graph for each of these. Oh, and show the orientation. Parametric equations have an order that they go in. And what I mean by that is, you know how when you draw like y equals x squared, what would that look like? Like a parabola, right? And I didn't move it around, so it's still centered at the origin. That's just it. Parametric equations have an order in which they go. So meaning like, does it start here and move this way, or does it start here and move this way? So we put little arrows on it to show like what direction it's going. And where we're headed towards is these are going to be motion problems, and you're going to have like velocity and acceleration and all that. And I keep forgetting to change this on here. It should say draw a graph of the following equations. I'm sorry. I'm sorry. They don't usually pass the vertical line test. They're not functions. I'm just so used to saying functions. I need to remember to go back and change that. But actually, it's important to bring up, and it makes me bring it up. So not necessarily a bad thing. But we're going to draw each of the equations and show the orientation. And then we'll eliminate the parameters. So we'll get x in terms of y, or y in terms of x, whichever one ends up being easiest. So you're going to make a little table off to the side here. You're going to have t, which is your parameter, x, and y. And typically you're told like where t is going to fall. So do you see how here it's -2 to 3? Like you're usually given that, like a domain, I guess, so to speak. So we're going to plug in all the numbers -2 to 3. And I usually do all of x and then all of y, so I don't have to keep switching in my head which equation I'm using. So let's do all of x. If you plug -2 in for t over here, what do you get for x? 0. We're just going to go down the row here. If you plug in -1, -3. If you plug in 0, -4, 1 will again give you -3. 2 will give you 0, and 3 will give you 5. And then we're going to do the exact same thing for the y's. We're going to plug all these in for t for the y equation. So if you plug in -2, -1, this will be -0.5, 0, a half, 1, 3/2. And it's going to go in this order when we graph it. So like there is what's called an orientation to them. And we'll put little arrows on it to show how it's going. All right, so we need our x's to go, like when you draw your grid, make sure you make it go far enough. I need x to go down to -4 and up to 5. So like make sure you leave enough room for that. And our y's don't need to go very far. Those are all kind of small numbers. Just make sure you leave enough room. And when you graph this, the parameter t does not get graphed. Like this is still an xy coordinate plane. T is simply the parameter. If you want to think of it as time, you can. Most often it is. But you're still going to just graph the xy point. So actually, let me move this up so you don't even see t anymore. So we're just going to graph those points, and they go in that order. Okay? So 0, -1, we're going to start right here. -3, -1/2. -4, 0. -3, +1/2. 0, 1. And then 5, 3/2, which would be 1.5. Thank you. You get mail delivered every block.
Every time. These are very important.
Well, you always have somewhere to be. Oh, I meant to hit pause on that, but I guess I didn't bump the button. Okay. Anyway, it's going to start here and go in this direction. So the way that we show that is with little arrows. And I put at least one arrow in between each points, so like each 2 points. So like it's going to go this way, and then it turned around and now it's going this way. And you can put more if you want. You can put extra ones. They look like little Cupid arrows or something. But it started here and the motion goes in that direction. So it starts here and then it goes around that way. Good so far? You have x in terms of t, y in terms of t, but when you graph it, it's still x comma y. Now, the directions also said to eliminate the parameter. That means you need to solve one or the other of these for t. And you want to pick the one that's easier. So which one of these looks like it would be easier to solve for t? Like get t by itself. Yeah, good, because this one has a t squared. I don't want to deal with it. How would you get t by itself there? What would you do? Yeah. Multiply by 2. 2y equals t. You're going to take that, substitute it in for t in the other equation. So it's just some algebra. So you'll have x equals 2y squared minus 4. And then we're just going to square what's in the parentheses there. So what will that give us? 4y squared minus 4. And because it's x in terms of y, do you see how we got an x equals and then a y over here? You want to write what your y values stayed in between. So our y values stayed in between -1 and 3/2. Do you see that there? So you're going to say that y stays in between -1 and 3/2. Again, it's like stating your domain. If we had y equals, and then like y was in terms of x's, we would say what x stayed in between. Lastly, you want to make sure it makes sense. Do you see how it's x equals and then you have a y squared? And do you see how it's a sideways parabola? Like, does it make sense? Like, I'm gonna like tie it all together there. Let's try another one. I made this one a little bit harder though, as a heads up, okay? It just says times or what? Yeah, bigger than -1. So from -1, and it can go on like forever, okay? So make your table. We want t, we want x, we want y. And I'm going to start at -1. And then we can put as many more numbers as we want. So I'd like, at least a few. But we do have a square root over here. So let's think about numbers that are going to end up like giving us something pleasant for the square root. So after -1 and looking here, what would be another like good number? So we don't end up with square root of something weird. 3 would be good. There's one before that. So we're going to do 3, but 0. So we're going to do 0, 3, and then can we maybe just get one more? 8. And then this is kind of like poor notation. And we are going to do some limits here, but I'm going to put infinity. You can't technically plug in infinity. We'll do a limit to infinity. But just to like see where it heads off forever, because it just says t is greater than -1. So it's going to go on like infinitely. Okay. We're going to do a good bit of limits here, which is good because it'll be review of limits. When you go to try to plug in -1, and I'm going to do all the x's first. Again, I like to do a whole column at once, so I don't have to keep switching between the equations. When you go to plug in -1, what happens? 0, which square root of 0 is 0, but the problem is that 0's on the bottom. Okay, so we're going to have to do a limit. It's going to be limit as t goes to -1, and technically it would be from the right. So you would put a little plus sign in there of this equation. What does a 0 denominator mean? What does that mean in the graph? Like, well, actually, let's review all of it. Let me go back. What does 0 over 0 mean is in the graph? A whole. If you have a number over 0, asymptote. Okay, this is back from unit 1. Okay, so when you go to plug in -1, you're going to get 1 over 0. And that means that there's an asymptote. It's either going up or going down, and you're just checking the sign. So since it's from the right, give me a number to the right of -1. 0. If you plug in 0 here, do you get a positive result or a negative result? Positive. So it's going to go to positive infinity. And again, that's poor notation really to put an infinity in a chart like that. But we still did a limit, so we technically used limit notation. So I'm going to like let that slide. All right. So that means going upwards or not upwards forever. If it's x, that means going to the right forever. Now let's plug in 0. If you plug in 0 to this, what do you get? 1. If you plug in 3, that would be, yeah, a half, because you would have square root of 4 would be 2. If you plug in 8, it would be a third. And if you go to infinity, again, I'm going to write it as a limit. Limit as t goes to infinity of this. Yes, it will be, but can I get everybody else there? You're right. I'm just trying to review limit notation with you. I'm trying to spiral in some of that review because it's back from unit 1. So why would it be 0? It is going to be 0, but why? Yeah, the denominator is bigger and bigger and bigger and bigger and bigger. You're going to get 1 gazillionth. I know gazillion's not a number. 1 trillionth, okay, which is super, super, super tiny. It's going to go towards 0. All right, we're going to do the same thing with y. As a heads up, we're going to do limits with this one too. Okay, fun with infinity today. If you try to plug in -1, do you see how it'll give you a 0 denominator? Okay, so we're going to do limit as t goes to -1 from the right of that equation. Limits are really just notation. Like it's really just learning how to write it. That's how they write it on the AP exam. Like when they score stuff, it'll be like 0.4 limit notation, you know, so you got to be able to write it. So if you plug in -1 for t, you're going to get -1 over 0. That means there's an asymptote. And so you just need to check if it's going up or going down. So give me a number to the right of -1. 0. If you plug in 0, and you only check the denominator, we're just checking the denominator. 0 plus 1 is 1, that's positive. But this is actually going to go to negative infinity. Why is that? Yeah, it's a negative over a positive, so negative, going downwards, okay? Now we're going to get actual numbers for these ones. If you plug in 0 to this, what do you get? It'll just be 0. It'll be 0 over 1, which is 0. If you plug in 3, 3/4, if you plug in 8/9, and then infinity you have to do as a limit. Gosh, you guys are good. Awesome. We know limits. Why is it 1? Right, because this is t and this is t. When it's a tie, what do you use? Coefficients, which aren't written, so they're 1. It's not always going to be 1. Like, what if there was a 3 here? Do you get what I'm saying? It's not always 1, but in this case, it is 1. Okay, so let's draw a picture. So I'm going to plot like the actual numbers first, and then we'll make sure that the like infinity stuff makes sense. You can kind of space your tick marks out for this because we have a lot of really tiny numbers, like fractions here. And again, I scooted my paper up so you can just see the X and Y. You don't plot the parameter. This is just still an XY coordinate plane. So we got 1, 0, that's right here. 1/2, 3/4. Okay, like there-ish. Do you see what I'm saying? Like good enough. 1/3, 8/9. So getting closer and closer to 0, 1. And then here we have 0, 1. But look, it's going to be an open circle. You can't actually put a point there. And why is that? Their limits. Like, well, yeah, you can think of it like an asymptote, like each one of these separately, but it's like headed towards there, but there won't actually be a point there. Okay. So it's going to do something like this. Now make sure this makes sense. As X goes to positive infinity, that's this way. Is Y going to negative infinity? That's this way. Is that making sense? Okay, don't put an arrow on the end of that though, because we have to put it in the correct direction. Like you can make this keep going. It can go to the edge of the paper if you want. But T is progressing this way. So your arrows should be going like this. And it's getting closer and closer and closer and closer to that point 0, 1, but it won't ever actually get there. So that's the orientation of the curve. And then we're going to eliminate the parameter. Which one of these would be easier to solve for T?
No, thanks. Oh, yeah.
I would go X. I know there's a square root and that's weird, but what's the difference? Like, why would this one maybe be easier? There's only 1 T instead of 2 of them. So let's try and get T by itself. All right, welcome back to algebra. How would you try to get T by itself? So, oh, good. I was hoping someone would say that. You're going to multiply this over and then divide the X over. So they're going to switch places. Swap them. I like that. That's what I'm going to say for you guys from now on. Swap them. Mathematically, you're multiplying the square root over and then dividing the X over, but just swap them. All right. Then what? Square both sides. 1 squared, just 1, and then X squared is X squared. And then minus the 1. So you're going to take that and plug it in for T in the other equation, and there's 2 places that you have to plug it in. And then there's going to be more fun with fractions and algebra and all that good stuff. It's going to be okay. So when you plug that in, you're going to have 1 over X, or Y equals, 1 over X squared minus 1 over, now this will actually be kind of nice. I know you're like, there's nothing nice about this, so we hate you. If you put 1 over X squared minus 1 there, and then have a plus 1, the minus 1 and the plus 1 are going to cancel. It's just going to be 1 over X squared. Let me scoot this up. And then what we're going to do is put these 2 together and then put these 2 together. I always draw it like that. It looks kind of like a little heart. So Y equals, now if you put 1 over X squared over 1 over X squared, it would be 1. The thing I would relate that to is, do you remember when you do the unit circle and you have square root of 2 over 2 over square root of 2 over 2? Do you remember that? and it just equals 1 tangent of pi over 4. Anyway, that's going to be 1 minus, now this would be 1 over x squared. It would look like this. Any thoughts on that? It would be the reciprocal, which would just be x squared. After all that, it came out to 1 minus x squared. Let's check if it makes sense. Does this graph look like 1 minus x squared? Like it's an upside down parabola moved up 1? I get we didn't get this part of it. Ooh, but let's talk about the domain. X has to be what? Just look at the x column here. It goes from 0 greater than 0, like from 0 onwards. And not an equal to, because we would have an open circle there because those were limits. Fun with fractions. This is why I was bringing up the unit circle. Okay, so go ahead and make your table and have t, x, and y. And again, typically you're given what, oh, I'm sorry, this one wasn't t at all. I'm just so used to putting t. What's the parameter for this one? Theta, good, sorry. If you put t, fine, like whatever. But... All right, and it goes from 0 to 2 pi, because that's the unit circle. So we're gonna do 0 pi, and then like we need some stops along the way. So like, let's pick smart ones. What do you think we should pick? Yeah, pi over 2, and then pi, 3 pi over 2, 2 pi. Do you want me to draw the unit circle up here for you?
I have it in my head.
You have it in your head? You don't need me to draw it? Okay, then I'm going to trust you. So what is cosine of 0 pi? 1, good, times 3, 3. Cosine pi over 2.
No, 1. It's 1 half. 0.
0 times 3,
Oh, yeah.
0. This is why I wanted to write it on the board.
Negative 1. Wait a minute.
Cosine of pi is -1 times 3 is -3.
Then 0.
Then 0 again. And then back to 3. Now we're doing sine. Sine of 0 pi. 0 times 4, 0. Sine of pi over 2, 1 times 4, 4, 0, -4, 0. We got it. Okay. And you're just going to plot those points, and basically you just need to get the orientation correct. And we're not going to eliminate the parameter for this one because it would just be like, to get theta by itself, you would have to do a cosine inverse or an arc cosine or a sine inverse or an arc sine. We're just not going to do that, but we are going to graph it. All right, so you're going to start at 3, 0 here. I'll scooch this up so you can just see the x's and y's. So 3, 0, 0, 4, -3, 0, 0, -4, and back to 3, 0. So it's an oval, and it's going to go in this direction. Yeah, well, you know, you didn't have a grid there. It's okay. Just do your best. And what I want to draw your attention to is, if the 3 and the 4 weren't there, cosine is x, sine is y. If the 3 and the 4 weren't there, it would have turned out to be the unit circle. Do you get what I'm saying? You would have 1, 0, 0, 1, like it would all be 1s, 0. Like it would just be the unit circle because cosine's x, sine is y. So technically, you've really done parametric equations before. The whole unit circle is 1. Cosine's x, sine's y. They're both in terms of theta. All right, write parametric equations for the following function for the given t. Okay, so we have this I made the first one as easy as possible. X is t. Like when it says write parametric equations, you want to have an x equals and a y equals. X just is t. So what would y be? Don't overthink it. Perfect. I made the first one like super. And I threw a derivative in this one so we could just do like one little bit of calculus today. All right. T is dy dx. So you're going to have to do the derivative of this. So what is the derivative of this? Negative 2x. Now I need an x equals and a y equals. That's the goal here. So how would you get x by itself? Because I need that for my x equation. Good. So negative a half t, or negative t over 2, I guess, however you want to say that. And then how would you get y? Well, you're going to take this negative a half t, plug it in for x. So it'll be y equals, I'm just going to do my work off to the side here. Y equals 1 minus negative a half t squared. And I'll put my answer over here. I just wanted to put a box around the answer, like nice and neat. So it'll be 1 minus, and if you square that stuff, well, first of all, if you square a negative, it's going to be positive, but it's still subtraction because it's 1 minus. If you square all this stuff, what will you get? Good, 1/4 t squared. So if it says to write the parametric equations, you need an x equals and a y equals.